Pretty much everything we have translates pretty much across most languages you'll encounter. Okay, there's no new language structures involved. All of these features are basically implemented as libraries in whatever system that you are operating in. And a lot of the work is going to be using these various libraries. And there's a lot of functionality in these things, and they are pretty large. So there's no hope of me being able to, in lecture, kind of go through all of the functionality of, say, the Java Windows system or any Windows system, or today the I/O system. All of the systems I know of implement pretty much the same metaphors for each of these ideas, but their syntax and the exact routines they call is very different. And depending on the system you're working in, you just have to fight it out and learn from the documentation. Which brings me to another kind of general point. A lot of programming these days and software development, since we're building quite large systems, is gluing together or using components from other people, either system libraries as in Java or as in Windows, or you might be trying to use some open source libraries that you download. For example, if you're writing a system that wants to talk to web servers, you'd like to have some library, some way to deal with the HTTP protocol and the URL standards and all that. And believe me, you don't want to write that yourself, because it's pages and pages and pages of standards, and you won't do it as well as the people who have spent years doing it. So you might as well take a standard library like WinINet for Windows or the libwww that W3C puts out, incorporate that into your system. So you get a lot of incorporating other people's libraries into your system. And a lot of doing that is just figuring out how they work, since the documentation on these things is pretty uneven, let's say. Some of it's very well documented, some of it's not documented at all, some of it's documented but the documentation's wrong. So you need to you just have to have patience, and you have to read the books if there are any, use the documentation if there is any, and then just try things out. And just try and figure out enough about these systems, whatever you're doing, to accomplish the task you're trying to accomplish without trying to incorporate the whole thing into your mind. You don't need to learn the entire Java 2D graphics system, for example, to write any given graphics program. So once you have the idea of it, a lot of programming is just looking through the manuals, figuring out which particular thing you have to do at the time. And a lot of times you get stuck. Either the library doesn't work as you expect, or you don't know quite how to do this. And a good thing to do then is to turn to the net. There's a lot of people out there using these libraries, especially the more common ones. And if you get stuck, the best thing to do is to go on Google or some search engine, or a lot of these packages have news groups associated to them, and search on your question. And usually if somebody has come up with, if you're stuck on something, it's probably hard. Somebody's probably put some effort into solving it, if it's a common enough thing. And people tend to post their answers when they do that. And so you can, usually tap into a discussion about why this routine doesn't work as you expect, or how to do this using this library. And it's just amazingly helpful. Conversely, if you run across something that nobody's commented on and solve it, definitely write up something and post it someplace on the internet or to a news group to help your fellow programmers along. So the first one of these topics that we're going to talk about is Stream.io. Okay? Up to now, we've been working with programs dealing with classes and methods and stuff that basically take data that we've already kind of built into our main program, and it futzes it around and manipulates it a little, and then maybe at the end prints out an answer. And there's only so many interesting programs that you can write that way. That's kind of a write-only metaphor, and you quickly run out of interesting things to do. So the next thing you want to do is be able to get data into your program and write interesting data out. And the metaphor that is everything is kind of converged on for doing this, and this is pretty uniform across languages and systems, is something called Stream.io. Okay? The Java Stream.io library is quite complex. It has like 60 classes associated with it. But the basic concept of what it's trying to do is quite easy. Something like C would have maybe 2 equivalent of classes, or just maybe 8 routines you would have to learn. Okay? 8 methods you would have to learn, because it gives you a very general mechanism for doing everything. Whereas Java tries to give you a whole mess of components, each of which do a tiny, tiny part of it, and then you glue them together to make the tool that you want to do. Or you choose the one from column A, one from column B. So what I'm going to do in the first part of the lecture is talk about the general stream metaphor and some of the issues there, and then give you a tour of the Java classes, what they're trying to do, what they were thinking about, and then, you know, at least it should help you navigate the book and the documentation. So, all right, so here's our program. And we want to get data into and out of it. One question is, where does the other data come from? Well, it can come from the terminal, or where does the data go? It can come from another, a terminal, which is essentially the Xterm or console window that you would have on your PC, on your screen. Or, you know, a lot of you are using Emacs as your compilation and run mechanism. That kind of makes everything look like an extra level of magic is going on. But all Emacs is really doing is forking off essentially a terminal in the background, running the program, catching the output, and just displaying it in its window instead of the terminal window. So that all really counts as a terminal. And a terminal is kind of an odd thing, because it's basically this, you know, we have these cool window systems now, but the terminal window, the console window, is basically an implementation of a metaphor that goes back, you know, to the beginning of computing pretty much. It's a very serial connection, and it really is implementing a CRT, or even more primitively, a line printer terminal connected via a serial port to a main computer. So it has the metaphor that you're sending data one character at a time to the terminal where it's being displayed, or you're pushing keys and it's sending data one character at a time to the computer. Okay? So even though we have this fancy window system, we've still carried forward this kind of CRT metaphor from probably the late 60s. Other places where data can come from and go to is files. We have file systems, and we want to read and write those. Network connections, okay? We want to be able to read and write from not only our local file system, but remote file systems, or, you know, talk to the internet. We might want to read and write to other programs, all right? The Unix pipe mechanism is a nice example of that. You're allowed to, you know, say, cat the one file through, say, grep or some filter, or just concatenate, make a pipeline of files on the Unix command line. And what that does is it hooks together the input and output of programs so that the input of one goes into the output of the other. And it's very handy. If you have a GUI-only environment, you tend to miss being able to do that, to be able to concatenate programs. One thing that is also interesting is strings. Often it's very handy to be able to read and write strings as if they were like a file. So you'd like to build up this big string in memory as if it was a file, and then maybe do something with it afterwards. What the stream idea, the goal of the stream idea is to basically make all of these things look the same to your program, which is a nice idea. It means you don't, when you write your program, have to know whether it's connected to the terminal or a file or a network or other programs. You can just write in terms of the basic stream operations, and you set up when you set up the stream, you connect the other end to one of these, and everything just works. And what a stream is the basic metaphor for a stream is something like a garden hose or a pipe for data. Okay, it's a very physical metaphor. That's why I draw this kind of hose-like thing here. And the basic idea is you put data in here, and it kind of pushes all the data along that's already in here. And eventually, if somebody reads out of here, you know, it gets to the other end. Consequently, you can read data, pull data out of this pipe. And like some kind of hose or stream metaphor, once you pull something out of the pipe, okay, it's no longer in the pipe. You've got it. So if you pull something out of the pipe again, it's going to be a different thing. All right? So that's really the basic stream metaphor. And when I say pull things out of these pipes, pretty much universally, the thing that you pull into and out of streams at the lowest level, the very lowest level, is bytes, which are 8-bit chunks of data. And presumably everybody knows what bits are from 6004. So basically we put in, at the lowest level, we put into this pipe and pull out of this pipe uninterpreted 8-bit chunks of data. So the basic universal operations on streams, there are basically 4. Open, all right, they're not always close. Read and write. All right, this is what you can do on streams. The open is sometimes implemented as a method called open. Sometimes it's implemented, it's buried inside a constructor. For if you're using an object-oriented system, you bury it inside a constructor for your stream. But basically, you want to open, and this argument represents the target, whatever type it is. So you say open a stream on the terminal or on some file or on this network connection or on some other program. You know, open can be pretty complicated just because the number of different targets you can get. And this will return you something, and you don't have to worry about what, and it's going to be an object in Java, but in other systems it'll just be some random thing that you think of as a stream. Close is pretty easy. You take any stream that's been opened and you close it, which basically shuts down this pipe and the communication channel. The open basically finds the thing you're trying to talk to and builds up one of these pipes so you can talk to it. Close just shuts the thing down. Once you've done a close on the stream, you can't do anything more with it. So the other 2 ones are read, which, aside from the stream, usually takes a buffer and a count and returns int done. That's not a good call. That's not a good name. Okay. You give it a stream, whatever that is, that you want to read on. You give it a place. You give it the number of bytes that you want to read from the stream. And you give it a place to put these bytes, usually an array. So this says, read the next n bytes that are in this stream and put them here. Okay? And the return value is usually the number of bytes that are actually read. Okay, one of the properties of this is these guys are putting data in this end of the pipe. You're reading it out this end of the pipe, kind of asynchronously. Okay, and so you can often do a read. Say you want to read 1,000 bytes of data from the pipe, but say this side has only put in 500. All right, what the system does is it will say, okay, here's 500. You asked for 1,000, but here's 500. Okay, so it's going to read up to this amount of data, but not necessarily all of it. And finally, we have write. I'm kind of writing these all out in kind of a static style. If we were doing object-oriented style, it would be like stream.read byte or buff and n. That's how you would do it that's how most of the Java routines work, but this is kind of the most general form. Same types of arguments, a byte array and a count, and pretty much the same return. So what this says is to take n bytes out of this byte array and push them into the stream and return the number that you were able to write. Okay? It's much less frequent that that write is not able to finish all of its bytes. Since usually these pipes have a little bit of squishiness in them, you can push bytes into them even if this guy isn't taking them out. Okay? If you have a network connection, you might eventually fill it up. Okay? If you have a network connection to some process or program across the internet, and it's reading things very, very slowly, and you're writing things very, very quickly, eventually that whole pipe is going to fill up. And after a while, it won't let you push any more data in until some data empties out. Because if you think about it, you're pushing in data into this pipe, and you don't want the data to get lost. Once you've pushed it in the pipe, semantically, your program can forget about it, but the guy on the other end still has to be able to read it. So it has to be somewhere. And the only place it can be is the technology that is implementing this kind of physical pipe metaphor, which means that somebody somewhere has to be able to store all of the data you put in. And if you can just, you're basically using up resources that somebody else has, either disk or memory or wherever they're putting this. And they're not going to let you basically do a while forever, write data into this pipe and just take it all. Eventually going to say enough, and your write will back up. If the connection breaks or you're unable to open the file, if it is a procedural language like C, it'll return an error code. If it's a more sophisticated language like Java, the equivalent things here will throw exceptions, which is why we had to do exceptions yesterday, because all the stuff in Java you have to wrap in exceptions handling. Any questions so far?
Yeah, the parameter list for read and write
doesn't
seem to correspond to what's in the notes. I'm wondering
what's in the notes.
Has the array for
Oh, I just changes the order. This is just a very, very general. This is not syntax that corresponds to any particular language. So, but the types of the things that you need are universal. They're going to be represented different ways and in different orders. But basically, you need the thing that you're writing on. You need a buffer to get stuff from, and you need a count. Okay, so this is very, very generic idea. This is syntax that's probably not particularly applicable anywhere.
Well, what do these commands open and close really do? In other words, why they're necessary?
Well, what open does, and as I say in Java, it'll be buried inside of constructor, is somehow you have to get this pipe, right? When you start up your system, you don't have any of these connections to anything. So if you want to write to a file or read from a file, you've got to set up one of these pipes to the particular file that you want to talk to.
Well, what does it mean set up a pipe?
Um,
How come that wouldn't be if I just say read? Why?
because what are you going to read on? You say read on some file, a file name, you mean?
But you can have more things open, right?
Yes, yes. You can have more than one pipe open, certainly. More than one of these streams open.
Also, there's only one. So if I open another pipe, if I open another target, I'll
Right.
create a new pipe.
You would get another one of these. You get one of these for everything that you open. Okay, every time you do an open, you get a new stream, which you can then write to. So you can open,
So you can really only have one thing coming in, even though it's kind of.
right, each one of these streams is really a point-to-point connection between your program and something else.
So you cannot share the pipe.
You cannot easily share the pipe. Okay, once you've opened it, okay, and you have this pipe in your program, you can give it to other parts of your program within the process. You probably can't give it to other programs in general. Okay, there's probably systems in which you can do that, but that gets into some very hairy stuff. So, but think of simply each stream is just a point-to-point connection between your program and some destination that you want to talk to. It's like a phone call. Okay, you can't start talking on the telephone till you dial, right? And the other person picks up. So the dialing and the other person picking up is essentially the open. Close corresponds to the hanging up. Okay, and these are like you listening and you talking.
So the open statement will contact the target and say, ask if they're there. The target will say, yes, I'm there.
Pretty much, yeah, pretty much. And of course, that has to happen in different ways for each one of these types of things. And all that is like buried, so you don't have to worry about it. Like for the file system, it'll make sure that the file is actually there, okay, and that you have read permission or write permission, depending on what you're trying to do, before it'll let you open it. For the internet, it'll make sure that the network is up and the connection is there. The machine you're trying to talk to is willing to talk to you. So each one of these opens is doing a lot of stuff under the rug, but all you have to worry about is the open part, the dialing part. Yes?
But where do you specify what you want to do with this stream that is going to check whether you have write or read permission? Because here you are just giving it a target and you don't mention what you want to do with it.
That's true, and that's a little less general. Sometimes you specify in the open, okay, sometimes you would specify later on. That is a detail which I've glossed over, but it's true that in a lot of times you want to specify in the open command whether you want to open something for reading, writing, or both. Certainly the open command in the C library has the file open command has two arguments, the file name and a little descriptor saying open it for reading, open it for writing, open it for both. Don't want to get too much in that right now. Okay, an important issue with I/O that's very different than everything you've come up with so far is one of the properties of these read operations on this pipe. Okay, say we have a stream connected to the terminal, all right, and we do a read operation for a character. But nobody's typed anything yet. Okay, so there's no data in the pipe, in the stream, and we're trying to read data. Usually what happens is that the read will not return. Your program will just get stuck in this read forever, or not forever, until somebody hits a character. So this is mostly, you're used to now, procedures or methods that you call, they do some computation, they either fail and you crash, or they return with the value. Here's a routine, a method that you can call that is going to wait for an arbitrary amount of time before it returns. Okay, this process is a common thing. It's called blocking. Okay, so read is termed to be a blocking routine if when there's no data available, it waits for data. Okay, your program, if it called read and is stuck in read, is said to be blocked or blocked on read, and so it's just used as a general verb in that sense. Very important concept, and something a new idea that's something to consider, because once your program is here, okay, and it's waiting for this character, it's not doing anything else. For example, say you did have two streams open, one of which was on the terminal, okay, and one of which was to a network, and somebody's trying to send you stuff over the network. As long as you're waiting for this terminal input, nothing else can happen. And in that, even if there's data available here, you're not going to get to that part of your program until the terminal returns, this read returns, which means not until somebody types. There are, in some systems, non-blocking versions of read that you can set up through some rigmarole where you can tell read, even if there's nothing there, I want you to return with a nRid of 0. Java does not do that by default, but often you will get another stream command that in Java, yikes, I'm just spelling all wrong. Is called available. And in other systems is called something similar. And you basically call it on a stream, and it tells you how many characters are available for reading, or whether there are any characters for reading, or if you called read, would you block? Okay, so if you really don't want to block in your program, you want your program to remain responsive, you would first test to see if there was anything to read, then before you called read. Okay. Later on in the course, we'll see fancier mechanisms to avoid blocking or getting permanently stuck on in I/O and retaining responsiveness. But something to keep in mind. It's
In a program that uses blocking, any minimum amount of data that I feed the program will unblock it?
yeah, one character is enough. And the reason I think that this evolved is it's initially programs that communicated with a single terminal and nothing else. Before there was networks, before there was anything else, it was just easier to write the program to wait for a character. Okay, that lets the operating system put that process to sleep and go use computational resources to do other things, as opposed to, if this guy returns 0 when there's nothing there, you got to do, and you want to read something, you've got to wrap this in some loop that says, while this is not equal to 0, and just keep calling read over and over and over again, and that's going to just burn up your CPU. So that's why blocking reads are good. Yeah.
Well, does it close after the first character is read, or does it stay open so that?
Does the stream? The stream stays open until you do a close or until something breaks. So you can do lots of successive reads and lots of successive writes. So everything works until you do a stream, until you do a close.
You have to know how many bytes you want to read before you ask for it.
Yeah.
Really?
Well, if nothing else, you have to know, when you do a read, you have to know where you're going to put them, right? And since you have only a finite size thing of where you can put them, you don't want to ask for more than you can fit in that space. So typically you would, make an array of size 1,000 and then say, okay, give me 1,000, and maybe it'll fill up that whole array, maybe it won't. If you just say, give me everything you have, it could be more memory than your system has. So.
And if you have a stream to the terminal on the internet, you can be reading from them both at the same time.
As long as nobody blocks, yes. You can have two streams, one to the internet, and then you just have a loop that says, read some from my terminal stream, read from my internet stream, or you can do an echo loop, and like read from your terminal stream and just write whatever the person types out into the internet stream. So, very general mechanism. It's very nice in that it makes everything look the same. Yeah.
If you call it with an argument 0 for the number of bytes to be read.
Yes.
If you call it with 0, what will it do?
Usually, and this is a very system-dependent thing, so you got to check. Usually, it'll return immediately with a red of 0. It will not block on 0 bytes, but very system-dependent sort of thing. So definitely check, or at least be aware. Okay, one other general concept before we get into Java. Okay, maybe two more general concepts before we get into Java. The idea of buffering. Okay, at the lowest level, what our program does when it does a read, say we do a read, and say we're doing character-to-time processing, so we are just basically reading 1 byte at a time. What the lowest level of read is going to do is go to the operating system, whoever it's talking to, and say, give me a byte. And that'll pull a byte out of this pipe and return it to you. Now, the amount of mechanism that's involved in getting that byte is just enormous, okay? Because it involves your program talking to the operating system talking to whatever mechanism is involved here. And so there's a lot of work involved, okay? And if you do that for that amount of work, for every byte you read, your program is going to run very slow. So one way to do that is to amortize that overhead of doing the lowest level read over a lot of bytes. So, you always read big chunks of data, or as much as is available out of the pipe. So that reduces the overhead of this low level read. On the other hand, sometimes that's very inconvenient to structure your program that way. So most systems will put something, give you a facility in between called buffering. Okay, and what buffering is the system will kind of give you a little safety net here on every pipe, and it will let you do your stream calls on these things that look exactly like streams. Okay, so these are just little connector streams. Really, they look like streams on this end. As far as the programmer can see, they look the same. But what they're going to do for you is whenever you ask for a read of a single byte, say, it's going to go out and it's going to get a big chunk, okay, and always keep like a pile of stuff around so that when you read from this buffer that's kind of locally kept. And so it keeps that whole low-level mechanism. The expense of that, it amortizes it. So you pretty much want to run buffered reads. Most systems like C or C++, the buffering is done pretty invisible. You don't have to explicitly request it. In Java, you have to explicitly request it. There's very few circumstances where you want unbuffered reads. The only time in my experience I've ever wanted unbuffered reads is in the really old days when you were writing kind of interactive character games on CRT terminals, where you have the little X character running around on the screen, in which case you want it to immediately respond to characters when you typed. Typically, the buffering, one of the effects of the buffering is that characters will not get from your terminal to the program until you type carriage return. Okay? Typically, it doesn't send every character. It'll wait till you send character return, do the buffering, and that lets you do, like command line editing or input editing, right? If you weren't doing that, then every time you typed a character, even if it was a mistake, it would get sent to your program and all of that. So now in Java, you do have to ask explicitly for buffering. So in all of your I/O stuff, you're going to have this extra gimme buffering thing all over the place. Before we talk about Java, in order to understand the way the Java library is organized and the problem it's trying to solve, we have to talk about one of the problems it's trying to solve, which is data formats. Okay, if we think about what we want to write into files and what we want to read, it's basically the data types that we have in our program. For example, our basic data types like ints, floats, and basically text strings. All right? So these are represented in some way in Java. All right? What else do we have over here that's interesting? Strings, chars. Right, ints, we decided we said were basically 4-byte quantities in Java, internally represented. Floats were 4-byte quantities, doubles were 8-byte quantities. And so we need to be able to get these, read these off of files or off of this network. But remember, all we can read off of the network is individual uninterpreted bytes. So we have the problem of we have this int, which is a conceptual thing which, we want to make, but all we can do out of the stream really at the lowest level semantics, are read and write bytes. So the most straightforward thing to do is, okay, I have an integer I want to send to somebody. I know it's 4 bytes. I just send those 4 bytes over the pipe. And so somebody sends me an integer. They're going to send me 4 bytes. I then take those 4 bytes and somehow, magically, and in C you have to do this by hand, in Java it happens under the hood, you assemble them into a 4-byte integer. You take the 4 bytes that you get in some byte array and you assemble them magically to make an integer. Okay? All's well. But here's a problem. Here's something to think about. What order do you assemble the 4 bytes that you get out of the pipe to make the 4 bytes that you get to integer? An integer consists, if you look in memory, an integer should be represented as 4 contiguous bytes. So it's pretty easy to just say, write here, write it here, write it here, write it here, and maybe it'll work. It turns out that different machines represent their represent integers, not in Java, but in their native form, in different orders. So in some machines, the low order byte goes here, then higher order here. In other machines, it's exactly the reverse. Sometimes it goes that. There's really basically 2 types of machines these days, and they go by the name of big endian and little endian. And it's not Indian with an I, it's endian with an E, depending on what order the bytes are arranged. So in the worst case, you have to know, if you get a binary file with a bunch of integers in it, and you need to do this low-level read, in the worst case, you need to know what kind of machine that file was written on in order to properly interpret it, and have separate routines somewhere in your program. Your make int routine has to do different things depending on what machine it was written to. Java nicely hides a lot of that from you, and Java is good. It hides some of that from you. It's consistent in that Java running anywhere will always write its data in the same format. Okay? Whether the native format of the machine is that format or not, it will always write in kind of Java standard format, which I don't remember whether it's big endian or little endian. I don't know whether it says in the book. I don't know whether somebody knows. That sort of helps the consistency problem if all anybody in the world used was Java. Okay? If people use things other than Java, then you've got the same problem, and Java lets you, I think when you're initializing in your open, essentially, or your constructor, lets you say whether you anticipate this to be a big endian or little endian ordered file. There's also, when you're talking to the network, you have the same problem. There is a defined network standard byte order for integers. I forget which one whether that is big endian or little endian, but that's nice because at least all network connections should behave the same. Not everybody is so graceful as to follow that, but.
Can you read and write custom objects in Java?
You can, but at some point you have to break them down into bytes. So basically you have to first break the object down into its individual instance variables, and then break those down into a set of bytes in a prescribed order, and then ship them off. That process is known as serialization, or sometimes as marshalling. The process actually of taking a bunch of bytes, okay, and then compiling and then composing them into one of your high-order data types, that's known as marshalling, or the reverse of taking one of your high-order data types, turning it into a byte stream. This is, if you have to do this by hand yourself, it's just a lot of tedium. It's not terribly hard, but it's tedious. Fortunately, Java does hide some of it from you, but it's something you need to be aware of, and especially the fact that there's different formats. Strings are another matter, okay? If you're reading text files, okay, you want to read text files, things out of text files, and turn them into strings in Java. Okay, here we have another set of format issues. Most text files, if you write in English, in Emacs or something, just type a file, are stored in what's known as ASCII or ANSI format. Basically, each character takes up 8 bits in the file. And they're in sequence in the order in which they type them, in the order in which you see them. Okay? Java internally uses 16-bit characters because it wants to do something, use something called Unicode internally, so it can deal with non-Western languages, non-Western fonts like Japanese or Chinese or Korean. Your Emacs, unless you've fitted it up very special, will look at one of those files. If somebody wrote, say, a Japanese file, we're using this different encoding, it'll look like gibberish to Emacs. But so Java has this conversion problem as well, since it's not going to, all these editors are not going to start writing Unicode or 16-bit characters. For one thing, if you're writing English, it's a factor of 2 in size every time. It has to do a bunch of conversion to take normal text files that people write and turn it into these either 16-bit Unicode characters or strings, which are just concatenations of 16-bit Unicode characters. Later on in the course, when we're doing cultural stuff, I'll talk about the whole mess of character sets, character encodings, and the problems of internationalizing your program. But for now, all you have to know is that Java uses these 16-bit characters, and so there's this conversion process that has to go on, which Java will handle for you, but accounts for, again, some of the complexity of their system.
Do these things have to be done by bytes? Does there exist mechanisms for doing things bit by bit? For example, if you're in a compression program or something that needed?
Well, you read and write routines pretty much uniformly work on bytes. What you do when you compress is you first assemble it into a byte array, then you ship out the byte array, since the byte arrays are completely uninterpreted. All right, now I just want to give you a tour of the Java library. We know the problems now it's trying to solve and what it's trying to do, so we just need to get kind of our heads around what decisions they made and how they tried to do it. So the first thing to know is that being Java, they did it all with objects. So a stream is an object, and the read and write calls are method calls on the object. Okay? And the very lowest level stream is something, an abstract class called input stream, okay, which is abstract, so you can't really construct one. But if you had one, since it's an abstract class, there's a lot of subclasses, and you can instance one of the subclasses. So if you had one of these guys, you would call your read routine as s.read. And then the buffer to put it in, and I'm not sure this is the right order, so don't quote me on this. And then int n. Shoot, ran out of space. So the only point here is that since it's an object, we're using method calls stream.read instead of passing in the stream as the first argument as if it was a static thing. So the first thing, the Java library consists of 60 classes. They're explained. There's a nice picture in the book which just overwhelms you and doesn't really explain anything. But let me give you kind of a tour of most of it. So at the top level, they made 2 splits, okay, and then pretty much duplicated almost everything in each of the 4 groups represented by these two binary splits. So that immediately takes the number of classes you have to think about from 60 down to 15. And the split is input or read and output. And then binary and text. Okay? So unlike many systems, since Java has this native Unicode internally, it has to do a lot of this character set conversion from whatever the file is into its internal format. And that seemed to be interesting enough or complicated enough that they gave us separate classes for dealing with text files or binary files. The downside of that is, of course, you have to know what kind of file you're dealing with ahead of time. Though, a lot of times files are tagged either by their extension or sometimes by a magic number. The first bytes or so of the file tell you what type it is. So you could open it as a binary type, read the magic number. If it was a text file, you could reopen it as a text file. So the basic class up here, the basic high-level thing, and all of the subclasses are basically have extensions or prefixes on these. So you have input stream, output stream, and input text they call reader. They don't call it text stream. They call it reader. And output they call writer. Okay, so these are the basic high-level units. And so anytime you see like data input stream, data output stream, file input stream, file output stream, buffered input stream, buffered output stream, buffered reader, buffered writer, okay, those are all subclasses of these big kind of parent classes. And this is the split that they're trying to make. Okay, so basically everything is going to be duplicated. Almost everything is going to be duplicated 4 times. Okay, with these suffixes. And this is how to interpret the suffixes. So if you want to do open something, if you want to read some binary input, you need one of these. If you want some binary output, you need one of these. As I said, a lot of systems will give you a stream that you can both read and write on. In Java, you need 2 streams. Even if they both point, say you want to read and write to the same file or the same network connection at the same time, you still need 2 separate streams. And we'll see when we talk about networks that if you open a network connection, it'll give you attached to it one of these and one of those. So you just get it. Yes?
Do we need to use special precaution if we're reading and writing at the same time? Since we've got 2 pipes open, as you just said, one of them could modify right where we're trying to read.
It depends what it is you're writing to. If you're doing it to the terminal, they go to really different places, right? The reads come from the keyboard, the writes go to the screen, not a problem. Internet, those full duplex connections, not really a problem. Files, big problem. Okay, if you're reading from a file at the same time you're writing to it, you're right, things are going to get gobbledygook. So that's something that you want to be really careful about doing. Yeah?
Could you go over the binary text distinction again?
Okay, the binary text distinction is really whether the thing that you're trying to read from or the type of data you want to read from is basically text, strings, English, Japanese, whatever, or whether it's binary data. And binary data being say we took a big integer array that we had in our program, and we wanted to dump that to a file, not by turning it into text that people could read. Okay, so instead of turning the number 1 million into 100000, okay, which would take like 6 characters or 6 bytes of data, we just wanted to dump the individual 4 bytes that made up that integer. Okay, we could just take that memory image, dump it right on the file, and that's a binary file. Okay, binary files are pretty much when you take whatever memory representation you have of an object and write it into the file. And if you look at it with an editor or try and read it, you can't. It's just numbers in the file. So, and since Java handles these significantly differently, it makes the split. Most of the programs that you write are going to deal with text, and so you'll be spending most of your time here. Yeah?
What would a .class file be? Would that be binary?
A .class file would be a binary file, yes. Another source of binary files is certainly uninterpreted binary data, such as the output of a compiler, okay? Or something that you've compressed, okay? Once you've compressed something, it's no longer a nice array of characters that can be read. It's just this array of bytes that need to be uncompressed. Like archives also have a lot of binary data in them. Images are another example of binary data. Okay, they're just all the different colors of all the different dots in the image. Writer will try and write to what it thinks the native text format of your computer is, so that if you write a file, open it with Emacs, it should be readable if it's all Latin characters.
It won't write it English Unicode?
No, when it writes out, it will convert to what it thinks the native format of your machine is. So otherwise, you'd have to have Unicode editors to see what it was you wrote. So that's why they have these classes. If it was going to write as Unicode, these binary classes would probably work for everything. But here, the cross product of all the different text formats or text encodings is pretty big. As we'll see, there's I don't know, probably dozens of actually different character sets and, several different encodings that you can use to encode those character sets. So,
The book lists them and it takes a few pages.
yeah, the book doesn't even list all of them, but it lists enough of them that.
Determines that the native format on your system is like some crazy variable.
Yeah, it's something in, something the Java runtime and the operating system communicate. In Windows, it's probably some deep registry variable. In Unix, it probably just assumes that it is it's probably a kernel compiled thing, actually. So you probably have to recompile the kernel if you want it to be native Unicode or something. All right. So this reduces us down from 60 classes to maybe 15 classes in each one of these little holes or squares. So what do these 15 classes do? Well, some of them tell you what kind of thing you want to connect to. Okay? So for example, we have a class called file input stream. This is not going to work, so I'm going to move this. Excuse me. Come over here where I have lots of room. File input stream. And these names start to get very long, and these the constructors that you have to build start to get very long. So, and the constructor to this would take a string, which would be the file name that you want to open. Okay, so this would try and open a file called myfile. And if it succeeded, return you a file input stream, which is a subtype of input stream. Which is connected to the file you asked for. if the file you asked for was not there or couldn't be read, this thing would return an error. Okay, it would throw an exception. So anytime you have one of these things, you have to wrap it in a try block. So, and there are equivalents for each one of these. There's file output stream, there's file reader, there's file writer. You basically give it a file name, and you get back, one of these things in the blocks. So there's a bunch of things that work like that. Okay, there's things to connect to files. There's equivalent constructors to connect to strings. Okay, you can make one of these readers that'll read and write from a string. That's kind of nice. You can, there's another one that's very handy sometimes that will let you open up and read and write from a compressed file, a zip file or a gzip file, and it will do it'll do the expansion for you automatically. So you can open a .gz file, and you can get the uncompressed stuff out by simply reading and writing. That's very handy sometimes, saves you from having to first go through the process of uncompressing, then read the thing, then recompress. So that's some of the classes of things in here are what to connect to. All right. There's another set of them that deal with what. Yes.
So is that equivalent to open? Or?
Yes. The opens, the equivalents to open in Java are the constructors. So whenever you construct a class, inside it's doing what other systems would do in an open.
And then return a stream? Or?
And then it returns a stream, right. So the actual code to do one of these things, which is, I'm going to erase this, because the code to do these things starts to really, really grow. So let's say we want to do file input stream. We want to read some binary file. So we do a file input stream f equals new file input stream of my file. All right, so now we have f, our file stream. Now, what we'd like to do is maybe add buffer. These things do not have buffering on them. The raw things that you get when you do a file writer, file reader, is unbuffered. And in order to be anywhere efficient, you need to add buffering. And the way you do that is to create a buffered input stream. Let's see, call it BF equals new buffered input stream Is this unbelievable or what? And the thing that you give this in its constructor is the thing you want to buffer. So the thing you want to buffer, you've already got this connection to this file stream. You just want to add some buffering on it. So you give it that. All right? Now, what you'd really like to do is read, say, a bunch of binary integers out of there. All right? So you'd like to have a routine, and there is one, instead of doing our raw, instead of reading 4 bytes at a time doing the marshalling ourselves, we'd like to have something high level that says read int, and it returns us an int. OK, so we do something like read I equals read int. Actually, we need a stream to call that on. So we'd like to call it on something dot read int. OK, I left a little space there because we don't know whether it's f or bf that we're going to call this on. And you know, we'd like to have something like this. And Java does indeed provide you with nice routines like that. But they're not on file input, and they're not on buffered input. They're on data input stream. So data input stream is something that takes an input stream and figures out how to do the marshalling. All right, so dBF equals new data input stream. Okay, and the thing we want to pull our marshal data out of is the buffered stream. So we give that the buffered stream as a constructor. And now we are finally ready to actually read something. So we can call, let's add a little more space here, int I equals dBF, our data reading buffered stream, or buffered data stream, however you want to call it, read int. And this will finally read 4 bytes out of that, assemble it, and put it in our integer I. So, pretty amazing. Now, a lot of times you'll see examples in the book or code written where people get tired of making up dummy variables for these in-between things. So they'll just concatenate the news. So basically, instead of this, they'll just take this whole expression and blow it into here. And instead of that, they'll take that whole new and blow it into here. So you'll get, you'll get data input new data input stream of new buffer input stream of new file input stream of my file. Okay? And since that won't all fit on one line, it's going to be indented very strangely, as you'll see some of my examples do. You wonder why they did it this way. You also wonder what keeps it from being phenomenally inefficient if every time I need to get some ints out, I have to first call the method here, which calls a method here, which calls a method here. And I don't know the answer to that question. Unless they are doing lots of cheating under the covers, this thing must be massively inefficient. The last line, data input stream, is what we need to get these nice marshalling routines, the things that take 4 individual bytes out of our stream and assemble them into an integer in the right order. Okay? So the thing that gives us that is there is an interface they defined called data input, which has things like read int, read float, read char, whatever. For all the basic types, there's a corresponding read routine. And in order to get access to those, they're not available on one of those, and not available on one of those, you got to have one of these. So you just add one of those onto the end of your pipe, and that gives you a whole mess of nice routines to read and write binary data.
Can you do anything with just a file stream or buffered input?
On those, you can basically do bf.read of you can just basically do our low-level read. You can read a pile of uninterpreted bytes. Sometimes that's all you need to do. Okay, if you're doing some fancy processing or some encryption or encoding internally, sometimes you just want to treat the input as some stream of uninterpreted bytes, and this is fine. If you actually think the guy is sending you a series of ints, you have to do that. Yeah?
If we call close on dBF, can we be happy that all of those things are going to be closed?
Good question. I believe yes. I believe yes. Since this guy has access to that pointer. Otherwise, it would be a nightmare, and you couldn't use the chaining syntax. You'd have to maintain all the individual guys to do that. So.
But by calling a close on dBF, it should not close the rest. Because you could have a dBF, you might want to use something else.
I'll bet you. I'll bet you.
Close on F might cascade down, but I don't think it'll cascade up.
That is a good question. It's true. If you are sharing that, it could be. What has to happen then, in order to make both syntax work, it must automatically close on garbage collect.
No, actually, I
Because I just did this an
Yes.
hour ago. It doesn't close on garbage
It
collection.
doesn't close on garbage collection. So you have to explicitly close it. Does it close if you close on DBF and do the
Well,
chain?
I have an mine's anonymous, and if I call close on
The outer one?
thing, yeah, it closes.
I see. So that must mean that if you do have a shared one, that this guy is good, and you close this one's going to be closed too. Okay, which is true. You can alias this lots of times, and as soon as anybody who's pointing to it does a close, it's closed. So you have to keep track of all that when you're writing your program. Good point.
When would you ever want to instantiate several different data input streams from a single buffered input stream?
That you probably wouldn't do, but you might be passing around these variables at various places, or sometimes be using the data input stream, and sometimes be using that, and you just have to remember to only close one of them.
Would calling close on one that was already closed?
Calling close multiple times doesn't do any harm, I don't believe. On the other hand, if you close it over here and another part of your program expects it to be still open and is trying to read or write to it, it's going to be surprised. So that's more the danger than closing multiple times. One thing to note, writing from the terminal. How do you connect to the terminal? Remember our friend system.out? Well, there's something on there, a public instance variable called system.in, and that's of type input stream. We don't know quite what type of input stream it is. But we can feed that into this chain. Okay, so we can start to make this chain from system.in. Okay, and system.out is just the output version of one of these things. Actually, system.out is a very strange thing, but it can be thought of as an output version of one of these things. It actually carries around a lot of stuff on it from previous implementations of Java for backward compatibility. But so let's take a look at how we would write some text to a file. So first we need a writer, and we need a file writer. Writer f equals new file writer of foo.out. And then we want some buffering on it. So we want to make a buffered file writer. Yeah, maybe we don't want buffering on our writers, but what the hey. I believe, oh, no, you're right. It's just called buffered writer, exactly. Once you've determined here that it's a file, these guys don't care that it is a file. I just wanted to write more stuff. Bf equals, I'm losing it, new buffered writer f. And finally, we want to be able to do neat things like, say, print an integer, say, and have it come out, as a nice string like 100 in text form rather than binary form. And unfortunately, our buffered writers don't have all those routines on them. The thing that has them is print writer. So we need to get a print writer. PBF equals new print writer of BF. And now on this guy, this has prints for all these guys, plus our old friend println of a string. And now we can do finally pbf dot println hello world. And what this should do is open foo.out and then put a buffered writer on it, put a print writer on it, and finally write hello world to foo.out. And of course, all these guys, we would need to wrap in a try and a catch for I/O exception. In case anything went wrong, like this file was not available or it didn't exist or whatever. Okay.
Is do the writers below print writer, do they deal most with arrays of characters then? The others, like the streams or arrays of bytes?
I guess I don't understand the question. What do you mean by writers below print writers?
The buffered writer and the file writer.
Oh, these guys, yes. These guys are assuming that, essentially, yes, are assuming that what we're writing is text, and it's going to go Unicode to native conversion, okay? At least that's what this guy's going to do. This guy is probably not going to do much except buffer.
If you're writing a file where you're doing like similar stream operations a lot, would you ever like create your own user-defined type that handles all this, or would that just give you one more layer of like slowness?
You mean create a something called buffered data input stream that just automatically did that for you? You might do that, but then remember, okay, if you did that, this data input routine implements this. The reason we're using that is because it implements this data input interface, which says read int, read float, read whatever. Okay, there's about 25 of these things, which means if you implemented a class and wanted to use them, you'd have to re-implement all of those guys, or somehow inherit from this and fool it so that those guys did the right thing. So it's tricky. There is a shortcut in here to do this, I believe. I think it lets you eliminate one of these steps. Maybe it lets you open a print writer on a file name and it fills in the rest. Or there's something on the writer side. Let's see. Other things to talk about. Input. Input's a bit more of a pain.
Should we always explicitly close these things after none of them? Is that?
Yeah, it's good practice to always explicitly close your files, because if then you somehow decide to extend your program to write a loop around things to do it over multiple files, most systems will only allow you to have a certain number of files open at a given time. Eventually, your program will stop working for reasons you don't understand, and then you'll have to go and figure it out and say, oh, I have too many files open. The reading equivalent of this guy, of print writer, is, I don't think there is a reading equivalent of print writer. So you've got to get a buffered reader, all right? And I think buffered reader, say we had one, BR. Say we had one, and that has something called read line, which gives you a string. Okay, so it basically has routines that let you read a line at a time, but it doesn't do any nice conversion. You can't say you have a file that you wrote a bunch of integers into, separated by spaces, or maybe one integer per line, okay, in text format so you could read it. So the file looks like, first line would be 100, next line would be 222. Okay, this is what your file looks like, and it's text. Okay, say you wanted to read these things back in as integers. you've got to do some work. Because first thing you've got to do is read this line as a string using readLine. And then you've got to use one of your string routines, maybe a parseInt. And I forget where parseInt lives, whether it lives on integer, so you have to do integer dot parseInt of that string that you just read, and that will finally give you an integer. This is just a huge amount of work to process some of this input. In a language like C, this whole thing would be like 2 lines. Now, say you have more than one line, more than one number on here. All of that whole line ends up in your string. So now you've got the problem of, I've got a string that looks like this. How do I get each of the pieces of it and then individually turn them into integers using that? And there's a utility class to let you do that. I mentioned it. The book talks about it, called String Tokenizer. Okay. They try and make up for the total lameness of this mechanism by giving you this String Tokenizer class, which you can then say, OK, give me the first guy, give me the second guy, give me the third guy. And you can say what it is they're separated by. So say you have things separated by tabs or spaces. You can say, give me the first tab separated field. You get it back as a string. You call parseInt or whatever on it. And you finally build things up. Okay. One more interesting class in that set is the file class. This lets you manipulate files themselves as objects, as opposed to connections to or streams. Sometimes you want to talk about just the file itself. For example, you want to see if it exists. You can create a file object of a certain name, which doesn't create a file. It just creates a file object. And then you can say, does this guy actually exist? And it'll tell you yes or no. If it does exist, you can say, is it readable? Is it writable? Is it a directory? You can say, I think you can delete it. You can create a new one. Okay, so basically, the whole set of structures for manipulating the file system as a file system, as opposed to the contents of files, is in this file class. This whole stream class is for doing this very general I/O mechanism. All right, that's about enough of that. Tomorrow, I think I'm going to switch the order of the next 2 lectures. Tomorrow, we will do graphics, and I'm hoping to get the screen up so we can actually show some stuff, so it won't be me trying to emulate a Windows system and drawing circles. Friday, we're going to do event-based programming and the beginning of how to run graphic user interfaces. Friday is a hard lecture. It's a new concept, a new programming paradigm, something that's a little hard to wrap your head around. And so I'm just going to warn you, come in very smart on Friday. You don't have to be very smart tomorrow, but you have to be smart on Friday.
Can you give us the notes ahead of time?